Okay, so today we're going to talk about heavy timber frame construction. So hopefully you've at least glanced at chapter 4 a little bit. We start with heavy timber construction, and what we mean by heavy timber construction is big lumber. Okay, so it's not the dimension lumber that's in the typical wood frame house. Okay, most people can equate this with, kind of the big cabins. You go to a cabin up in Tahoe and they have this, right? You see the open beam ceilings, that sort of thing. That's kind of the style of this. I'll show you a whole bunch of examples later on. But it's used commonly in commercial buildings as well. So we're going to talk about that. But before we get into it too much, I want to talk about kind of the history of heavy timber and why it's still around today. So the beginnings of heavy timber, we go to the kind of mud hut dwelling sort of things, right? But as we first started building, right, we would use these crude pit dwellings. Basically, we're going to dig a pit, so we're going to lower the floor right below the ground around it, and we're going to use some timbers to help prop up around us, right? And we're going to pack it with mud, and it's going to provide a relatively good shelter. Okay, so we start with something like that. As we move forward, right, we start to think about what are these beams and how do we use them, and can we use them a little bit more efficiently? Can we find beams that are a little bit better in the shape that we want, that sort of thing? So we evolve into crux, right, which are curved timbers. I'll show you an example in the next set. They're hewn by hand, right? So we're not in the days where you pull out your chainsaw and cut the tree down, right? We're in the days where you have hand tools and you carefully work the piece of lumber and that sort of thing. And so these crux are the precursors to what we do today with glue lamps, where we can intentionally curve a piece, right, and make a rigid frame. So they're kind of the precursors to that, leading into it. So here's our examples of our early dwellings, right? This might be something that you'd see back east, right, the early settlement type stuff. So a crux is this curved piece of timber. Okay, so what you would do is you'd go out into the forest and you'd look for a tree that grew slightly bent, right, that was about the right size. You cut that tree down, strip the bark off, and that would then become your braced frame inside your building, right? When it was harder and harder to find these exactly perfect trees, right, we moved to having straight members, but we're using a diagonal brace. Okay, so we're bracing the big post and beam with a diagonal. Okay, so all this is just big timber. Okay. So European traditions, so a lot of European buildings are this way, were brought to North America in the first kind of settlement, right? This isn't the history class, so we're not going to get into that too much, but it's important to know where it came from. And it was commonly used until well into the 19th century, okay? It fell out of fashion once we kind of found light frame, and it became a lot cheaper to use light frame, which we'll talk about next week when we do light frame. The interesting thing is it's come back in fashion now that we have better modern tools that can help make the joints. And we'll talk about that a little bit later. So we start with our basic foundation. Okay, usually it's a stone foundation with mortar. Okay, in this day and age it could be concrete, right? But back then it was typically stone. And there's a few key factors here. Okay, see this notch in both sides? Okay, there's a notch, and there's also these posts that are going to support the main girder, which is that main beam that runs underneath the floor. Okay? So once we add that on, let's skip to the next piece. Okay, we end up here, we've got our main girder that sits in one notch, sits in the other side, and rests on those two posts. Okay? After that, we're going to lay in the sills, okay, that are on top of the foundation, much like we would do today. And those sills have special notches in them that are going to receive, right, the floor beams or the joists. Typically, in heavy timber construction, we're going to use girders, beams, right, and purlins are going to be the primary vocabulary as opposed to joists, but joists are still okay. So I'm going to try to stick with girders and beams to indicate heavy. Okay, so when I refer to joists, I'm going to try to save that for the light frame so we don't confuse. Okay, so we put those floor beams in place, and you can see this here, right? We have a sill mortise, which is that notch cut out of the sill, right, there. And we've got the tendon, right, that goes inside the mortise. You get mortise and tendon joinery, okay? So there's our tendon, there's our mortise. That's going to fit inside and slide into place. And then this is going to span from this sill over to our girder and then over to the following sill, okay? After we have those, then we're going to put our flooring, right, which is temporary in the beginning until we get our next set of bents up. And then it eventually becomes permanent. Now the nice thing is that these drawings have all those indications of this is oak and this is oak and this is oak, right? So if we were building a building like this today, this would be extremely expensive, right? So we're going to use engineered lumber today, okay? So this is raising the first bent, okay? And a bent is basically this frame, okay? So there's our frame, there's our frame. There's actually two frames in this. And this is overall together being called a bent. You're lifting them up with what's called a pike, okay? Because in this day and age, they didn't have cranes to come in and lift your bents up into place. So you're going to use these pikes, and a whole bunch of people are going to come and lift that particular building or that particular bent into place, okay? So think about the labor that's involved in doing something like this. This is not something that you can just, you and your crew of 2 guys can do, right? You need more labor. You need all the neighbors to come over, right? The whole term of barn raising, right, stems from something like this, where you invite the whole community over, you provide them food, and everybody helps you raise these into place, because you need that kind of labor. Notice you have somebody over here, right, helping to lift it that way. And you've also installed what are called stays, okay, which are temporary boards on the outside of the building, such that when you push it up into place, you don't accidentally push it too far. We're jumping to slides here. No. We want to stay on our slide. Okay? So we have that stay so we don't push it too far, and it goes over the other side. So that's part of the process. We don't want that to happen. In this day and age, it's hooked up to the crane. It's not that big a deal. Okay? So we have a 2 brace bent. So our bent is the same. Okay? Here's our braces. Here's our braces. And we continue, and we raise each bent, right, into place. We get to this last piece, right? We've tied them all together. We now have our wood frame building. Okay, our heavy timber frame building put together, and we're going to move on, and we're going to put the roof on after that. Okay? So the challenge with this kind of stuff is that it's very heavy. It involves a lot of labor, right? So when the light wood frame kind of came into fashion, right, we went away from the heavy timber because of all the labor involved, right, and the fact that we didn't have cranes and that sort of thing, and we went to the light frame construction. The nice thing is, now we have things like cranes, right? We have computer-guided saws, right? We have laser guides, right? We have all these tools that can allow us to make this kind of complex joinery relatively easily. So we're going back to building buildings in this way. Okay, so it does, even though it's an old way, we're applying modern technology to it. Okay? Okay, so in terms of structural timber, right? Columns that are supporting floor loads, we're looking at 8x8s, right? So we're talking big lumber. This isn't little 6x6 posts that are on your deck, right? We're starting at 8x8 and getting bigger, okay? Beams and girders, we're looking at 6x10s minimum, but we can get up into the range of the glulam that I showed you, big beams, okay? The trusses are going to be made usually with 8x8s. Decking is usually 3 inches. Okay, so we're looking at very big scale materials, not something that's like the light frame, which is why we call it heavy timber frame. Okay, so here's a heavy timber frame building. Remember this one slice, one piece, what's that called? It's a bent. Okay, so we've got all these bents running through the building, and you see that unlike, right, our light wood frame, there isn't this smattering of lots of little pieces, right? It's big pieces, big column, right? Column row. Column row, column row, column row as you go through the building. Yeah.
I know this is a little different, but like if you have light frame construction, this is a bent. What do you call a light frame?
Usually it's just a wall.
This wall.
Okay, and you're going to tip your wall. It depends a little bit on the type of framing method you're going to use, but it's a wall, and it may be either a platform frame or it may be a balloon frame. We'll talk about the difference. But it's not called a bent. Okay, bent is in heavy timber. Okay, and sometimes when you raise these into place, you'll be raising, right, the truss that spans above that holds up your roof all as one. Right, sometimes you won't. We're going to talk about how you join those columns in just a second. Okay, so here we go. Right, we have one bent. There it is. Right, we don't have a lot of people working on this job. We have like 4 people. Right, but we have this clever guy that's in the crane operator's booth. Right, that's doing all the major work. Everybody else is just lining it up and getting it into place. Right, so we're raising this bent that we otherwise wouldn't be able to raise, and that's going to slide up into place, and that's going to provide our particular wall eventually. Okay.
It's like something
This here is some other part of the crane, and I don't know exactly. It's connected to this truck. This crane is lifting there. I'm not sure what this is doing yet. This was not a job I worked. It's just an image. Okay? Sometimes you need to tie pieces together, right? So we have a bent here, right? There's another bent that's over here. We need to tie them together, so this is the tie piece. Notice the fancy joinery that's done at the ends of these particular beams, right? So this notch here is going to match up with a notch there, and they're going to slide together, and then you're going to bolt, right? So all this stuff has to be really carefully considered before it's put up there, right? If we're in light frame, you get the standard size, you put it together, you put a couple nails in it, we're good, right? This is it's a much more complex frame to build. It requires more skill, and it requires more knowledge to be able to do it. Okay, you have to learn how to do all these joints. So the interesting thing about timber, okay, so heavy timber frame construction, is that it's considered to be a fire-resistant material. Okay, so if you have a big 8x8 or a 6x10 beam, and it's exposed to fire, the outside is going to char, right? But because there's so much material to it, it's going to be really hard for the fire to actually burn through and weaken that beam enough to fail. Okay, it's going to happen, but it's much harder. And so the interesting thing here, right, is that if you have a similar sized beam, steel's going to fail faster if it's exposed to fire than a heavy timber, right? So you would think, wait, wood burns, right? But it has to do with the size and the amount of material that you're working with. So it ends up being a very fire-resistant material. Now the problem is that a lot of times we blend heavy timber with light wood frame construction. And as soon as we blend the two, and I have a slide that we'll get to in a second, as soon as we blend the two, we lose that fire rating because we have the light wood frame. So we're down to that fire rating. So even though there's heavy timber in a building doesn't necessarily mean that it's a fire-resistant construction. Method. Okay? Fire-resistant process. So for this to be considered a fire-resistant material, the infill walls, right, the floors and that sort of thing, still have to be made of a non-combustible concrete, fire masonry, that sort of thing. Okay? So the infill panels, let's see if I have a picture here, right? The infill needs to be fire-resistant. So you have your heavy timber frame, the infill is fire-resistant material like brick. That's when it is a truly fire-resistant building method. Okay? So the problem is, as soon as you do something like this, right, we talked about the fact that wood inherently shrinks, right? You guys remember? Which direction does it shrink more? Tangentially. It's an impossible word to say, okay? Where does it shrink the least? Yes, the length, right? The length, right? So that presents a little bit of a problem because does brick shrink? No, right? So brick doesn't absorb water and expand or lose water and shrink. So you run into a problem if you have a masonry frame that's in juxtaposition with a heavy timber frame, because the wood's going to move around and the masonry isn't. So we have to think about how do we make these connections such that we don't have the building fall apart on us with that movement. Okay? So that movement is called differential shrinkage, right? If we go all the way back, see, I'm trying to review for you a little bit, right? The final's coming. If we go all the way back to the second lecture I did about foundation, we talked about differential settlement, right? Where certain parts of the building settle more than other parts, right? And it causes issues. It causes all those cracks that are in your house, right? In my house, at least. The same thing can happen here, only this time it's not settling, right? It's shrinkage of the wood versus the non-shrinkage of the brick walls or the concrete walls. Okay, so we have to deal with that in some manner. Okay? Okay, so we know that wood expands and contracts more depending on moisture content. The other thing to think about in this is the larger the beam, the longer it takes for changes to occur. Right? You have more material, it's going to take longer to dry out, it's going to take longer to shrink. So you may not, when you put it in place, it may be a couple years before it shrinks the way, as much as it's going to shrink. So you have to anticipate this out quite a distance. And so that's part of the problem. So we've devised a whole bunch of special connections that we'll see. There's outlines in the book that kind of go through them. I'm going to walk through them in just a second to avoid these problems. Okay? Pintles are the kind of major way of doing it, and there's split rings, and there's a whole bunch of other examples that I'll go through. Instead of listing them, we're going to go to the drawings. I'm going to try to walk through. If you can, I'd take a second and try to kind of make notes and draw a little bit on this one. I know these are hard. The images are in the book, so you can look at them later on. But I want to walk through and kind of help you understand what's going on in these images, because this is kind of critical to this construction. Okay, so what's happening here is we have a beam or a girder that's supporting our floor, and we also have a column that's running through. So this is a second story of a building, right? We need to support that second story. So this column comes up from the first floor, and it's supporting this set of beams. Okay? If we had this set of beams running, and we put the next column just on top of that set of beams, or on top of the flooring, on top of the beams, right? This beam and flooring would shrink, and that whole column would shrink, causing the floor to dip in that particular place. Does that make sense? Versus a masonry wall that's fixed. Okay, if we have the building where it's all wood frame, there's no masonry walls, we don't have to worry about it as much. But in this context, we need to worry about it. So, instead of resting this next column directly on top of this piece of wood, right, this next column is resting on what's called a pintle, which is kind of like an upside-down mushroom, so to speak. Okay? And so this is made of steel, right? The column sits in this steel square. This tapers down to a steel pole, so to speak, that rests on a steel plate, right, that rests on the column below. Okay? The beams and the flooring all slide around that steel pintle, right, that upside-down mushroom. It's kind of like a funnel-looking thing. Okay? All of this goes around so that this can shrink, right, and expand due to moisture, but it doesn't change the overall height of the building. The building stays the same. Right? So the floors move independently of the column stack. Okay? These little metal pieces are called dogs, right? They're just attaching the two sides of the beams together. Yeah.
Wait, so is that like, you make a hole so you can put that beam straight down?
Right. So the way this is actually, you could do a hole through this. In this context, they have two separate beams that are coming together. You can see the little joint line right here. Okay? When that's happening there with that joint, basically they're notching out one end, notching out the other end of the beam, so when they come together, they go around that steel post, so to speak. Yeah.
That seems fairly weak to lateral forces.
Doesn't it? Yeah. I agree. So, given that, right, we start to come up with other ways of doing it, right? And we'll talk about how do we, in the modern sense, how do we handle it, because we have some better techniques. So we'll get to that a little bit better. So as we move along, sometimes we want to eliminate all those weak points. So we move away from the pintle in this example, right? We have our post coming up with a steel cap to it. The next column comes all the way through and rests on this steel cap. Okay? So when we get to the modern way of doing it, we can make engineered lumber that's long enough so that we don't ever have to have a joint. Okay? But in this sense, we still have to have a joint. We can't have pieces long enough. So we have our steel cap, but this column comes all the way down and joins them together. Okay? Notice that this steel cap is now wider than the column itself. Okay? It spans from here to here, which gives us this nice little shelf, kind of like a half a bracket, that we can rest our beam in either side. Okay? We want to make sure that they don't come apart, so we're going to use this block, right, to basically tie both sides of the beam together around it. Same thing happens for shrinkage, right? Because these are independent of the column stack itself, these can shrink and expand separate from the rest of the building, which is always what we're trying to do, is to isolate that. Okay? Another example here, not as critical. This is a very old-fashioned way of doing it, but I'm just going to walk through it so you don't have to draw it or think too much about it, but I want you to be aware of it. In this example here, okay, we have these little lateral blocks, right, that are sitting underneath, right, the, if I can get my terminology correct, the beam, right, these little ledges, or ledgers, so to speak, are attached to the post with what are called split rings, okay, and this is kind of an old-fashioned way of doing it. The problem, okay, the reason that we came up with these split rings in the first place is, could we take a beam and could we take this little ledger and bolt the two together? Sure. Okay, but we're relying on the shear strength of that bolt not to shear off. Okay, because the bolt is the only thing, right? It's just like in steel construction, the bolt is the only thing holding that in place so it doesn't slide down. Okay, so what we've done instead is we've increased the amount of surface area, we've increased the amount of shear strength of that connection by adding this little ring of steel. Right, it's very simple. It's just like if you took a steel, one of those steel rings that we looked at before, steel pipes, right? You cut it into a thin little ring, you embed it half in one side of the wood, half in the other side of the wood, and it gives you a whole bunch more surface area for those two pieces not to slide past one another. Okay? Not nearly as common today, but I at least want you to be aware of what a split ring is. Okay? Very labor intensive to do, by the way. Okay, so we have another example here, very similar. The column again is coming down, resting on top of the other column here, right? We have our two ledgers here and here, right? Our split rings there are holding it. You get the idea. Okay, so this one's hard, but I need you to draw some pieces of it. So what I would do is I'd concentrate from the floor up here. The reason that I want you to draw these is just that you know the terminology. Okay, so I'm going to give you a little bit of time, right? These kinds of questions love to show up on a test, right? Because I like to know what the terminology is. Okay, so you have your column, you have your floor girder, you have your floor beams, right? And you have your finished floor that goes on top. This is the finished floor from below. We come up here, we have our roof girders and our roof beams, and we have our roof flanking. Okay, so this is all terminology. This is in your book. I don't remember what page it's on. 142. Right, so you can reference that as well. But I'm going to give you a second. This should help embed it in your memory. It's really hard to see here. I apologize. At least it's in your book. These are totally the drawings that when you're reading the book, you just flip the page and skip over. So that's why I'm making you look at it.
Okay. We want to know what roof girder is.
Do I care if it's a roof girder versus just a girder? No.
Okay.
As long as you understand that a girder supports a beam. Okay. And then the next slide that we'll see, we also have a coiling.
Okay.
Okay. And we'll get to that.
What is the girder?
The girder is this. Sorry, I have to walk up. It says floor girder here and roof girder here, right? But it's the primary structural element, and then the beam rests on top of the girder. Okay, it's similar to concrete, right? Where we had the girder and we had the beams. Similar.
A girder more like, kind of like a wafer, in a way, is going the same direction.
No, the girder's the heaviest member, though. You're talking about the waffle slab, right? Where we had those thin little
Well, you know how on a wall, study wall, you have the wafer going across, the WHA,
The whaler.
Whaler.
The whaler.
Yeah.
In concrete. It's in a concrete form. It's too small. I'd say it's too small. I mean, when
But
we
it's going
talk
the same
girder,
direction, though.
yeah, it's going in the same direction. But when we're talking girder, we're thinking big material, right? It's the biggest member in a heavy timber frame. you're not being graded on the quality of the drawing. Just try your best. Right? Let's save that for like 130 and 131. All right, I hear murmuring, which means that people are finishing up. Okay, so now we move to, you flip the page, right, and we wind up in kind of the first realm of roof truss that we've talked about. Okay? And so we've got a heavy timber frame roof truss here. I'll talk a lot about the details of trusses in just a second. The key is when we jump all the way up to the roof, right, we're changing from beams to purlins. Okay? So just think when you get to the roof, it's called a purlin. Right? I don't have a good way for you to remember what a purlin is. Just something that you have. It's a purlin. P-U-R-L-I-N. Purlin. And that's going across up here at the top. Okay? This particular piece could go on top of the other building if you wanted to. It happens to be a separate building, but it doesn't matter too much. You don't have to draw it. Okay? I just want you to make note of what a purlin is. Okay?
That's usually on top of the rafters?
Right. A purlin's going to go on the roof right, but running perpendicular, right, in between where the trusses are, right? So unlike light frame, where we have all the rafters and we have nothing on top, in this instance, right, we have our trusses, but then we need something to span in between our trusses, so we're going to span it with a purlin, and then your roof planking is going to go in the opposite direction. Okay, so a little bit different than the light frame. Okay.
When you say planking, you say like a plywood type thing?
The thing about it, I'm glad you asked that. So it says planking in the book, right? You go through all these. The floor deck says planking or decking. Here it says that's not usually plywood. It's usually, and I'll show you some slides a little bit later on. It's usually some kind of solid wood. Okay. If it's plywood or if it's a slightly different way of building up that floor, it's not in the same fire rating category. Okay, so as soon as you mix in some other method, you lose the fire rating. So in this instance, we're talking about all it is heavy timber, right? And there's some disadvantages to that. We'll talk about it in a second. But all it is heavy timber. There's no wall cavities. Okay, so this decking or planking is actually going to be thicker, at least 2 by, sometimes it's 3 inches. Not nominal 3 inches, but a full 3 inches. Yeah.
Is that one they used to use like a 2x6, like a tongue and groove type of wood?
Right, exactly. Exactly. It's like a tongue and groove. Sometimes it's even thicker than a 2x6, right? And then you can use plywood on top of that as your flooring material. But it's the plywood itself isn't thick enough to classify for the same fire rating. Yeah.
Like, you know how in like in South America, like they have even high-rise buildings, like 40, 50 stories, whatever, with concrete. They do have these, and also probably not scale in South America, like maybe in North America. But how high would they have at the highest, you know, anywhere in the world? They would have a heavy metal building,
You mean a heavy wood frame?
heavy lumber.
Ooh, that's a tough question. The problem is it starts to get too heavy for the amount of bearing capacity that it actually has. Right? It's not that strong in compression compared to, like, say, concrete or even steel. So it starts to get a little tricky. I don't have a good answer for you. You know, I'd say you could probably go 4 stories, maybe 5, but you're starting to get a little, it's a little iffy after that.
That's the same as light.
It's still very similar to light, yeah.
I don't know if it was in the book or I saw it somewhere else, but there's a 30,000 seat stadium in Washington that's made of a heavy timber truss wood.
I'm getting to it. I'm getting to it. You'll see examples. So you can, when we get to the new methods of construction and we start to hybridize beams and stuff, you can get some kind of bigger spanning things. So I'll show you some examples of that. But it's not usually in terms of height or number of stories. It's more in overall spanning capability. So when we get to the Tacoma Dome in Washington, right, you'll see that it has a huge spanning capability, which makes it tall because it's this giant arch, right, that's in wood. So it works, but it's not really about lots of stories. Does that make sense?
Yeah.
Okay. Okay, so the nice thing, right, we move into the contemporary world, right, our world, and we have things like the glue lamp that we talked about. We have all those engineered lumber products. Primarily in heavy timber frame, we're going to be dealing with glue lamp. Okay, that's the primary method. So we can end up making pieces that are long enough to span the distances that we need, right? So no longer do we have to have the giant tree, right, to cut down to make the piece of lumber big enough for what we need, right? We can make it up in smaller pieces. So we do stuff like this. This column runs continuously from the floor all the way up to the ceiling, right? It's one length. It's glue laminated, right? And all of the beams that meet this column, right, are also glue laminated pieces. So instead of having to have that pintle, right, or all that special connection of plates, instead the column runs continuously through, and these black things are steel plates that are helping to bridge the connection. Okay? And this, once you bolt it all together, starts to give you the lateral stability that you were asking about. Right? So when we add and we meld the steel plates with these kinds of connections, we can start to achieve the kinds of lateral loading conditions that are safe for us to build in, say, California. Right? So we have to think about that. So the other problem with this kind of construction is wherever timber beams join a masonry wall. Right? So if you have a concrete wall, you have a brick wall, you have something like that, and you have a beam that's going to rest on it or near it, okay? We have to pay very careful attention to a few key ingredients, okay? One is moisture, right? We know that concrete can absorb moisture, right? So it's going to have some water in it, If that water comes in contact with the beam that's embedded in it, right, it's going to rot and eventually going to fail. So that's bad. So we have to deal with that. Okay? We also have to deal with how do we fasten the beam to the wall so that it stays where it needs to be. That's a problem. Okay? And we also need this last condition. We need it to be able to rotate out freely so that if the beam fails, right, due to fire or something like that, it won't collapse the wall above. Okay? And so this in words sounds weird, but in illustration makes more sense. Okay? If this particular beam is resting in this wall, right, and it fits very nicely in the cavity, and something were to happen to this beam, right, say fire burns through it, okay, it fails for some other reason. When it fails, right, it cracks the masonry wall, and now we have the whole upper story collapsing, okay, which is what we don't want to have happen. So we want this to come out like this, okay, same beam, but this time we've cut the end on a taper, right, so that when it comes out, the upper end here doesn't lift up, right, and pop the top of the wall off. So we have to think about that. So we also have moisture, okay? So the way we handle moisture is we make sure there's at least a gap of a ½ inch on 3 of the 4 sides, okay? It's pretty much impossible to have a gap of a ½ inch on all 4 sides, right? Because one side has to rest because that's the nature of the beam, okay? Sometimes we'll slip in some kind of a pressure-treated piece in there, right, that'll help absorb any moisture that's there, not come in direct contact. Sometimes this will rest directly on the concrete. Depends on who's building and the local building codes in that environment. Yeah.
How big is the beam, you said?
At least a ½ inch, all the way around. Okay? If the beam is chemically treated, though, right, pressure treated, we talked about that last week, if it's, or 2 weeks ago, because of spring break, if it's pressure treated, right, then it's resistive to rot, so we don't have to worry about that gap. So this is if it's a non-pressure treated piece of wood. So that's how we handle that. Okay? So typically, there's a steel box beam, or a steel beam box, will be used to securely attach the beam, right? Or there's this other method, which is a little old-fashioned, right, where there's basically a little piece of malleable iron that's embedded in the wall that the beam rests over. I'll show you a picture of it in a second. Okay? In either instance, it still has to be designed, that box has to be designed such that when the beam fails, it'll still allow the beam to fall without kicking the top of the roof or the second story off. So here's an example here. Okay? This is that steel beam box that's embedded in the wall. Right? We have our masonry wall around the beam box. The beam comes in. Notice that this is tapered at the end, so that allows it to rotate out freely, right? And there's one set of lags here that's holding the beam in place so that it can't slide out, right? But if it were to fail, it allows it to pivot, right? And not pop the top of the wall. Okay, so that's one solution. The next image here is the old-fashioned way, okay? This is where you have that malleable iron piece that I was talking about. So there's no bolts involved in this. The beam sets in and rests over that little piece so it can't slip out, right? It's relying on the weight of the beam not to slide out. But obviously, there's no bolts of any kind, so it can freely rotate, okay, if it were to fail. So it's just the older way of doing it. Notice this little corbel here of the brick, as opposed to having the box that's square, right? This can be done as well, but it still has the taper such that it'll fall out when it needs to. Okay? So when we move into the world of contemporary fasteners, right, we're going to have much more steel involved, right? And in this case, right, we have our beam. We're up at the roof level right now. It wouldn't hurt you guys to take a little bit of time to draw these too. Okay, so we're up at the roof level because this will help you think of this, right? This is our steel bracket, right, that's embedded into the wall, right? It comes out with those 3 bolts holding it securely in place, okay? The taper is still here on this beam, so if this goes to fail, right, it's going to fall cleanly out, right? The bolts are fine because the bolts are outside of the pivot point, right? The steel's just going to bend. Too much weight on the steel. Okay, we've got a whole bunch of roofing that we'll talk about later up here, but it doesn't matter just yet. Okay, and then I'll walk you through what's going on over here once you have a second to draw this first section. We'll get to that when we get to roofing. a wall that extends above the surface of the building. Yeah, it's like a castle. You got the little parapet. Okay, so all I'm really concerned with is you've got your masonry wall, right? We've got our bracket, we've got our beam, it's gonna rotate out, we've got our taper, right? Don't worry about everything up above, doesn't matter. The Glulam, no. If it's one of the others, yes. The Glulam is still considered better than this because it still has the mass of solid wood. So I would say the ratio of glue to actual wood fiber is still pretty small. Very frequently they mix. The problem is if they start mixing that different shrinkage. Okay, think about that. You just have to anticipate. Exactly. Okay, so I'm going to start to talk about this last example, and then this is one of those impossible things because if I keep this off, you can't see what I draw, but if I turn this on, then you can see what I draw, so we're going to just have to flip back and forth. So I'll start drawing off for a little bit so you can see what's going on here, right? So in this particular example, I want to actually draw it for you so that it makes a little bit more sense, I hope, okay? But this is an intersection, it's like a T, but it's going in 4 directions, okay? So this piece, right, is a beam running, we'll say like this, and I will turn the lights back on. I know, it's just a problem, right? Okay, so that's this beam that we're talking about running in this direction. These two beams are ultimately going to be running this way draw straight, right there. This is going to be running this way, like that. Okay, and finally, we've got our column that's running underneath, right? That's coming up right in the middle of the two. Okay, right underneath it, supporting the weight. So, I'm going to flip it so you can see it again. Right? We have our intersection like this. Right? We have one beam running this way. They could be continuous. Right? This could be a continuous beam. This could be broken. This could also be seamed in the middle. Right? Doesn't really matter for the sake of what we're drawing. Right? So we've got this T working in both ways on top of a column. The trick here is that we have a special bracket, right, which are shown by these metal horseshoes here and these straps here, right, that occur and run underneath and back up and over and down like that. Right, this strap comes out. There's our little bolts. There's a strap on the back side here. There's bolts, bolts, bolts. We also have a nice weld here. We come out this way with another side. Don't worry, I'll turn this back on in a second. Alright, so we have a weld. It's in that corner. That. Back up right there. I'm going to flip so you can see for a second. Right, so we have this here is a steel bracket. Right, it goes back and up. This is that steel with the bolts through it. This is also a steel bracket. These are welded together on that corner. Right, this comes out like that. That's bolted through this particular piece. Okay. The tricky thing, right, is that this steel also comes down and attaches to this column. right? So this steel wraps around here, it wraps around here, but it's also welded such that one side or the other, forget which way I was doing it, it'll be this side, right, has a steel plate that comes down like this. Right, underneath that's bolted, you see the bolts right here and here, right, that's bolted through that column, right? So that steel, that fancy steel piece is actually what's allowing us to have this kind of a connection, okay? And it's also staying stable and very rigid, so it's handling lateral loading as well. Does that make sense? Right? So this is occurring inside the building, this is occurring outside, right, on the edge of the building. Does that make sense? Yeah, question? Right, this happens to be for the roof. I'm going to modify that drawing in a second to show you what happens further down in the building. Okay, so this is just at the roof because it's flat on top. Okay, so same thing here. We have girders running in both directions. We're going to have beams at some point as well. Okay, so this is occurring very similar to the last one that you just drew. I'm not going to ask you to draw it again, but I just want you to be aware it's the same kind of thing, right? We have this steel bracket that's nested into the wall, right? We have the taper so that the beam falls out as it's supposed to. Okay, very similar. Same thing right here, right? So the note here is critical. Column sections rest directly upon another to maximize vertical wood shrinkage, okay? So if we have a contemporary piece, and we're going back to this particular drawing, most of the time, this will be a glulam that's the continuous length of the height of the building, right? So coming out the top right here, going up that way, will be this same piece. It'll run all the way through. So this, right, this is a separate beam that's running this way. This is a separate beam that's running that way. It's relying on the steel plate. It's right there. Let me erase this guy. I'm going to try to clarify this drawing a little bit. There's the steel plate on the back side. There's our steel plate on the front side. Steel plate down there, right? So this is continuous. Continuous column, right? Runs all the way through. That's ideal. If they're broken, right, this will rest directly upon the column below it. Okay, to make sure that it's not going to shrink differently. Make sense? Right? We're not relying on the beams to shrink. Errol actually asked a great question while you guys were drawing, and he said, what about if you're mixing heavy timber and glulam? Okay, so glulam doesn't shrink because it's already dried and it's an engineered product. Heavy timber by itself will shrink. So if you're doing that kind of an environment, you still have to think through, if this is a glulam, right, I'm going to run it all the way through so I know it's not going to shrink. If these are heavy timber, they're still going to shrink independently. And we need to be aware of that when we design it. So you wouldn't mix, this is heavy timber and this is glulam, right? All of your girders, if they're going to be heavy timber, have to be heavy timber, right? If they're glulams, they all have to be glulams. And that's going to keep them consistent. Okay. This has to do with how do we deal with the metal fasteners? Did you have a question?
Yeah, well, like, heavy timber, like, I guess you would say the board, feet, or whatever, they just go as long as the tree is, or the way it, like, let's say, if it's 50 feet, the tree
Right.
has to be 50 feet, when it came out of it?
If not bigger, right? So that's the problem with heavy timber and why we've gone to glulams, okay, or engineered lumber. Because if it's heavy timber, right? So say we're doing just a large beam, so it's a 6 by 10 beam, okay? We have to have a tree big enough so that we have a clear 6 inches by 10 inches for however long we want the beam. So say it's 50 feet tall. So we need a tree that 50 feet up in the air is at least 6 inches by 10 inches, right? Can accommodate that. And part of the problem is we really want a tree much bigger than that because by the time we mill off the sides, right? If it's just right through the center of the tree, we're going to have that core and it's going to bow and twist on us, right? As opposed to if we were able to carefully conceive of where we cut that beam from within the tree itself. Okay? So these are,
Heavy timber just go as long as the tree and no longer.
heavy timber is as long as the tree and no longer. Engineered lumber can be longer than the tree because we're laminating pieces together. And so that's the key.
Is that different than glue lamp?
No, that's what I'm talking about, glue lamp. Okay, so engineered lumber is some of the other pieces that we've talked about, but in the heavy timber world, the only thing that is used is the actual glue lamp. Okay, because it's still a big mass of wood. Okay? So these have to do with metal connections, okay, and these are kind of a variety of different methods. I would say split ring is almost never used in this day and age. It still says it's a contemporary practice, but it's not as common, okay. This is just showing you how we try to attach pieces together. A lot of times we want to have these bearing blocks underneath so that these two pieces rest on the bearing blocks. This is just notching out, right, the column, so to speak, to accommodate. So you're creating bearing blocks because you've notched the column. This has bearing blocks attached. This has the split rings, right? And this last piece here is you've got bearing blocks, you've got split rings. It's kind of combining everything together. Okay, the truth is that we're moving away from that and we're moving into the realm of more just solid metal plates or fasteners. Okay, so this is an example of a truss, and we don't want that big ugly steel plate on the outside, so we've actually embedded the steel plate inside, right, the lumber, and we've bolted it through. So in this particular concept, these three are the steel plates. Okay, those three fit inside notches that are up above and notches that are in this particular piece, so that when you assemble it with these long screws, right, they run through the steel plates, but all you get are these little holes, not the big plate on the outside. Yeah.
All those screws that are sunken into the wood, right?
Right, they'll be countersunk into the wood. So you could, theoretically, instead of having all these, you could putty them all, right, so you wouldn't see them. So this is a way of hiding the steel that's involved in connecting these, right, but it's still there. Very commonly, when you have connections like this, right, the one that we drew, a lot of times, anytime there's a beam or something, they'll have fins that are inside like this that you can't normally see, right? And so even if you're bolting through, you just have another piece of metal that's helping hold the whole thing together, right? So this kind of hidden steel plate is very, very common.
Can you go back to that a little bit?
Yeah.
Is there another piece of wood on top of that?
Up here?
Yeah.
I'm guessing not. This should be just a glue lamp, right, like this. This slides down inside, right, and these slide over the top. It's possible that they put a trim board on top. I'm guessing not, because this looks like it ends right here. It doesn't continue. So this should be the top of the beam. Okay. Okay. So I tell you what. Let's take a break. We'll take a 10-minute break. So we'll come back in 10. We'll continue on with floors and roofs, and then we'll talk a lot about trusses, and I'll show you a whole bunch of examples at the end today. Okay.